Hello everyone, my name is Jiali Zhang, Technical Service Engineer at Park Systems. I hope you have been enjoying this year's NanoScientific Symposium so far. Today I'm going to present you a demonstration of Park MX10. We'll be talking about scanning ion conductance microscopy, aka SICM liquid imaging. In this session, I demonstrate how to acquire the topography of a relative soft biocompatible samples in an ionic solution with nanoscale resolution using SICM mode. SICM, which is a non-invasive AFM scanning technique that utilizes a poured glass pipette as scanning probe instead of a conventional silicon cantilever to generate high-quality topographic image of the sample. The biomedical research community finds this minimally invasive glass pipette-based scanning techniques is suitable to study the fragile biologic samples. For example, it allows for precise categorization of nanoscale structures and potentially lead to a breakthrough in cancer research. For this demonstration, the sample is a silicon-based organic polymer called polydimethylsiloxane, or PDMS. The biomedical and tissue engineer field use PDMS frequently as it is highly compatible with biologic tissues. On the macroscopic level, this PDMS sample is relatively soft and has a rubber-like texture. The sample is 150 nanometer high and has micro blocks with a 10 micron pitch that can serve as XYZ calibration guide on the microscopic level. In Park SICM, the AFM-Z scanner accommodates the glass pipette probes in similar ways as it would for a silicon cantilever probe. However, unlike the conventional AFM feedback mechanism, which is based on light diffraction at probe, in SICM, the Z scanner responds to an ionic current flow through the nano opening in the pipette. The operator inserts an electrode into the pipette after filling it with an ionic solution. A secondary base electrode connects to the immersed sample, completing the circuit, and the voltage bias is then applied. At the pipette near the sample surface, the current flow drops due to a restricted fluid flow. The Park's SmartScan automatic features allow the operator to select a target current or set point. The Park SICM automatically adjusts the bias to match that target current. Approach retract spectroscopy mode, or ARS, is an option for SICM. In ARS, the SICM pipettes approach the sample surface several times at each image pixel, measuring the current difference between the real-time current and the set point. When the difference falls within a specified threshold, the height is then recorded. Thus, SICM can generate the sample topography pixel by pixel. For the image acquisition, I'm choosing a poured glass pipette with a 20 nanometer diameter opening, such as an ionic current can pass through it. The size of the pipette opening determines the lateral resolution, and that the nanoscale opening is suitable for the high-resolution topographic imaging. For this demonstration, I use Park NX10 AFM system. The NX10 can accurately render high-resolution data due to its advanced decoupled three-dimensional scanners. The XY scanner moves laterally while the Z scanner moves vertically. All Park research-grade tools can perform SICM. In particular, Park NX12, which is a varied version of Park NX10, can incorporate an inverted optical microscope, which allows the operator to properly position a sample or log through transparent samples. The operating software for this AFM system is called Park SmartScan. It incorporates many automatic features, which makes it the easiest to use AFM system on the market. With Park SmartScan, even novice can obtain high-quality AFM images with the push of just 3 buttons. Park SmartScan allows the operator to select a targeted current or set point. Assuming ionic current flow is adequate, the system will automatically drive bias to match that target current. Once the current is steady, the SICM mode for Park NX10 automatically moves the pipette probe towards the sample surface until it registers current flow equal to the user-defined set point. AIS mode automatically counters the current drift effect, which can happen during measurements. In this mode, the SICM pipette approaches the sample surface several times at each image pixel. The current difference threshold between the real-time current and set point is about 2% by default. When the measured current falls within the threshold, the height is recorded. The SICM image continues pixel by pixel, thereby removes the dependence on the constant ionic current flow from the bus. This creates a stable image setup over time. Other useful smart scan features are available, such as image offset and automatic tip lifting to move to other sample locations. The image taken here is 40 micron by 40 micron scan, taken in skip scan mode, which will reduce image time by half by skipping the reduced scan. The image is 256 pixels by 128 pixels, and the pattern features about 150 nanometer in height with a 10 micron pitch. In this case, the total image time is approximately 12 minutes, but setup and image process in this video is shown at 8 times faster than the actual speed. Park Systems image analysis software XCI treats the SICM image identical to an AFM image. XCI can apply a flattening process to bring out the real topography. Its 3D rendering and enhanced coloring capabilities provide a more realistic view of the sample topography. XCI also conducts line profile analysis that can render the cross-section height profile. Here we can see the repeating pattern structure on this particular sample, which are 162 nanometer in height with a 10 micrometer pitch as expected. This concludes this demonstration on how to obtain nanoscale topography image in an ionic solution environment using Park Systems SICM. Park Systems would like to thank you for your time in viewing this demonstration. For further information, please visit our website at parksystem.com. We'll now proceed to a Q&A session, so feel free to ask any questions.